Okay, now we come to one of the most interesting things we can analyze and use in our circuits, even with the limited linear analyses that we know how to do so far, and that's the operational amplifier. The operational amplifier is a linear element, so we know how to use it already. So to begin, it has a differential input, so the result is going to be the difference of the two input leads. That's also what leads to the operational part of the name of it. And then the output is with respect to ground, so it's how far V out is above ground that is measured. And that is going to be some large multiple of the input differential voltage. So we can say that V out then is A times V plus minus V minus. Now, usually the power leads of this circuit are suppressed. We don't draw them. But if we draw them all in, then we see that we have to give it a negative supply and a positive supply. We can make some slight adjustments that you can look up, but we're not going to talk about here. And that V out is actually explicitly the difference between ground and this lead. Note that ground, since we don't draw it in there, is halfway in between the two powers. If we don't have any other reference, some kind of op-amps have an explicit ground connection as well. But usually it's just halfway in between the two powers. So the gain A is large. It's usually a couple 100,000 times this voltage. So this voltage would be in microvolts, and this voltage might be in hundreds of millivolts or something like that. That's the usual range. The input resistance, that is how much current will flow between here, is controlled by a very large resistance, usually on order of 2 mega ohms, which means since these voltages are small, not much current will flow in real op-amps. Finally, the output resistance is very small, which means that even if we draw a lot of current out here, the voltage will not drop. So just to show you an example of an IV, well, not an IV characteristic, but input versus output voltages. So if I put the input voltage here and the output voltage there with respect to ground, this is the differential input voltage, and I set A equal to 2, I get something that looks like this. Now notice, if I make the output too large, if I make the input too large, then my output gets saturated. That's because I can't get more than 12 volts out of this circuit. I can't get more voltage here than I put in. Right? Where would that voltage come from is what you can ask to remember that there's limits. If I increase the gain to 10, say, it looks something like this, and notice now that this line where it's linear is nearly vertical, and I can keep going. I can give a gain of 100. Here I've changed the y scale, the x scale to be 10 times magnified, and can still barely see this line. That said, that where you are on this line is usually going to be determined by something other than the input, and that's what we'll talk about next. So moving on to an ideal op-amp. So since the gain A and the input resistance are large and the output resistance is small, let's take the ideal case where those large and small things are pushed so that the gain is infinite, the input resistance is infinite, and the output resistance is 0, and let's see what happens in that case. Well, this infinite gain only is workable if we take some of this and connect it to the input to the negative input, which gives us negative feedback. In that case, the infinite gain will actually be very useful for us. And remember, it's not really infinite, it's just very, very large. And that means that the output is, well, we'll see what happens. So to analyze this, in this case, with negative feedback, these conditions are just for the case of negative feedback, that the input and the V plus and V minus have to be the same. Why do they have to be the same? Well, if they're different than 0, the difference of them is different than 0, then the output will be infinite, either negative or positive, or actually what you would say it's on the rails, the power voltage plus or minus 12 volts, say. So if that's not the case, V out is not pegged, then the input has to be 0. Second, no current can flow from one to the other because there's an infinite resistance, basically an open circuit connecting the two. Using just these two rules, we can analyze any circuit with an op-amp that involves negative feedback. Let's do the very simplest case, which is that in this case called the voltage follower. Notice here we have the feedback, right? Whatever the voltage is here, it's fed around to the input voltage on what's known as the inverting input. Right? The two inputs are known as the non-inverting and the inverting input. We know it's negative feedback because we're feeding the output back to the negative input. So in this case, we can consider two voltages. The input voltage with respect to ground of the positive, right? We don't have this lead because it's been taken away by the feedback. And the output voltage, which is the same output voltage we had before. And let's use our two rules to figure out what happens. This is what it would normally look like. We would just put in V in and V out. So in this case, we know because there's just a direct connection that the output voltage here is the same as the input to the negative terminal. And now we also know that V plus equals V minus, which means V in must also equal V out. Or, to say it the way it really works, V out has to be the same as V in. So what happens, V in has some value, V out had some other value maybe at the beginning, and if it was bigger than V in, then it went down very quickly until V out was the same as V in, and then it stopped correcting itself. That's how negative feedback works. You take some of the output and feed it back into the input. So if V out were larger than V in, we'd have a correction down because of the negative sign. And if V out were less than V in, it'd have to go up because of the negative sign. And it works out that it'll always stop when V plus and V minus are the same, which is the same as V in and V out are the same. So what good is this? Well, it's good because the input voltage here is very high, and the input resistance here is very high, which means no current will actually flow here. So if we have some very small charge on a capacitor, it'll just sit there. Whereas here we can drive a lot of current because the resistance is so low. The power to drive that comes from somewhere other than the input. So this acts as a buffer between the output and the input, but the output voltage is the same as the input voltage.